Hi everyone, can you hear me? Thanks, Tim. I hope the audio and video is clear. Let's start the class in a moment. So, I think in the last few classes we have seen about convolutional neural network. In the initial class, we have seen some of the applications of CNN. We have taken some data sets from online, and then we did some Resnet models, and we made some predictions, and we got some outputs. So those are real applications. And then what we did is we dive into convolutional neural network and try to understand the building blocks. In today's class, we will review what convolutional neural network is, and we'll try to understand everything through visualization. So for today's class, I'm going to use a simple dataset, MNIST, and there is another one more dataset, Cipher10. So MNIST is a grayscale, and this Cipher10 has RGB color, and this MNIST has around 50,000 images, and Cipher10 is 60,000 images. So this MNIST shape is 28 by 28, 1 comma, which is channel, and cipher is 3 comma 32 comma 32. So what we are going to do today is this MNIST has 10 classes from 0 to 9, so which is just some numbers. Let's say this is 3, and this is input image, and the output label is 3. Likewise, we have another image 7, and the output label is 7. So what we are going to do today is we are going to build a convolutional neural network from scratch using PyTorch, and then we will try to understand what each kernels inside this neural network. I'll explain what kernels again now. So what each kernels is doing when you pass some new image. So that's the goal of today's class. So if you are new to this class, I'm going to quickly explain what a neural network is in 5 minutes. Here is very quick overview. Let's say you have lots of data. This data also has output. I'm going to call output as y and input data as x. And then you pass your data to the model. Initially, model has weights and biases. Which is random numbers. Then we can get y prediction. By using y and y prediction, we can calculate the loss, and we take a gradient of the loss, which means how much will a loss change when I change weight and bias a little bit. If I increase weight a little bit, what happens to the loss? If I decrease weights a little bit, what happens to the loss? Our goal is to minimize the loss. So gradient tells that. Then we do gradient update, stochastic gradient descent. Then these random numbers will be more meaningful when you train a neural network. So we have input x and label y. By using x and y, you can train a neural network to create some model. The model is just a trained weights and biases. So model, I'm going to explain one more thing, architecture and model. So what is architecture and models? Usually architecture is like a structure. So you can create any architecture like normal neural network with some 10 layers or CNN or recurrent neural network. Architecture can be anything. So this architecture has weights and biases. These weights and biases are initially random and then trained by using the data. One second. Okay. So architecture is just a structure, and you use the data to train your model. Once the model is trained, you will get weights and biases. So together, this corrected weights and bias and architecture, I call this as model. So we know what is model now, what is input data, output data. We also know the predictions. Then loss. So there are two types of losses. One is regression and classification. In regression, we mainly use mean square error. For example, my model says the output is 4 and the truth is 8. What is the loss? Mean square error. I need to subtract 4 minus 8, the whole square. So this should be 16. Let's say I'm repeating this for 10 data. Then I divide 16 divided by 10. Then loss is 1.6. For classification, we use softmax. So this is a multi-classification loss. Softmax means at the output you will be getting like, let's say you are going to predict some data like MNIST. For MNIST, there should be 10 category, 0.2. Let's say the output is 2. So we'll get maximum number here, 0, 0.1, 3.7, then 0.01, likewise. So here this is 2. So we are getting maximum weight here. Remaining weights should be very less if the model is trained very well. Then what you do is you take exponential of each numbers and then divided by sum of exponential of each numbers. So you will get maximum probability for 3.7 and very less probability for remaining numbers. So this is softmax. So I think we have spent a lot of classes previously explaining these things, but now I am going to do a very quick overview. That's why I'm explaining it very, very fast. So in PyTorch, there are, for classification, there are two types of losses, cross entropy. This cross entropy takes real value, which we call as logits. So another loss is negative log loss. NLL loss. In this negative log loss, it expects log softmax. So we mainly use cross entropy, both are same. Cross entropy is negative log loss with log softmax. It expects log softmax, but for cross entropy, it expects logits. If you don't understand, if it's confusing, we'll see in the code. Okay. I think we have got some good overview of neural network. So now we are going to create a simple neural network, convolutional neural network to train this datasets. And then meanwhile, we'll understand what each weights are learning. We'll do some visualizations throughout this exercise. If you have any questions, you can ask on Slack. I'm not going to monitor YouTube, but if someone posts any questions on YouTube, please post it on Slack. I think Kalyan Jam asked, explain what is the use of gradient and what exactly it does in convolutional neural network. He asked what is gradient and what is the use of gradient in CNN. So let's say I'm going to explain very simple problem, x and y. This is 1, output is 2, 2, 4, 3, 6, 4, 8. This is very simple relation. If I ask you what is the output when x is 5, you can say this is 10 because you learned some parameter here. Here the parameter you learned from this data is w equal to 2. But computers don't learn like this. It randomly assigns some weight. It starts with some random number like 0.1. For 0.1, it calculates the loss. Then based on the loss, it tries to calculate the gradient. So gradient is just the slope. Also it's called derivative. So if you take, when w equal to 0.1, if you take gradient, you will get a huge number. And then you multiply w minus learning rate gradient. So learning rate is how fast you want to go in some particular direction. Let's say this is 0.01. So after some training, this W should be 0.2. Then it slowly increases like 0.3 and it stops when W equal to 2. When W equal to 2, you will get very less gradient. So when you multiply this, you won't get any effect. So you stop your training. So in this small example, y is equal to wx. Here w is some parameter. In the same way, in convolutional neural network, let's say this is number 7. You create lots of kernels. I will explain kernels soon. But in kernels, kernel contains weights and biases. So each kernel has some weights and each kernel has some bias. So here in simple problem, there is only one parameter, but in convolutional neural network, we will have many parameters, weights and bias. In the same way, how we learned this number 2, our model will learn some parameter here. That's the use of gradient in convolutional neural network. Maybe one kernel is good at predicting whether this image has any horizontal edge or vertical edge, those kind of things. We'll see in visualization shortly. Okay, so the goal of today's class is use MNIST dataset, then create a simple convolutional neural network. While doing convolutional neural network, I'll explain all the building blocks of convolutional neural network. We have already discussed this many times, but I'm going to do very quick overview. What is kernel, pooling, stride, kernel size, max pooling, activations, then fully connected network. Then we will do visualizations. We will do visualizations to understand what each kernel is doing when we pass some input image. Let's say this, if I pass 3, what each layer is doing when it sees some image. That's the goal of today's class. We'll see some coding now. So we are going to use PyTorch. I'm going to import PyTorch. So before that, this is Google Colab. So Google Colab has some free GPU, and it's like a Jupyter notebook hosted on Google servers. If you have a Google account, you can use it. Just simply type in Google Colab. Click Google Colab. You will see some screen like this. Then click Runtime. Change runtime type, hardware, GPU, and choose your RAM. So if you are using free version, it should be standard. I'm using Google Pro, which is $10 per month. So with $10 per month, I'm getting some high RAM and better GPUs. So it's okay if you don't have, it's not an issue for this class. Then click connect. If you have any questions on this, you can take a screenshot and post it on Slack. We'll answer. So it's connected. So I'm getting like 25 GB RAM. And you can see what GPU is by typing NVIDIA SMI. Typo. So it says Tesla P100. So I'm going to use PyTorch. So import torch. So torch has neural network toolkits. So I'm going to use import torch.nn as nn. Then we are going to load datasets using PyTorch. So import, I think it's Torch Vision. From Torch Vision, import datasets, transforms. So we are doing some transforms. For example, when I load some dataset, that dataset should be like some image file. I need to convert those image files to numbers so that I can do some matrix multiplications. So doing lots of matrix multiplications and adding some activation layers is all about neural network. So it's just a matrix multiplications. It's not exactly matrix, it's tensor, because anything greater than 2, anything greater than shape 2 is tensor. So this is tensor multiplications. So that I'm going to use datasets and transforms. Then I'm going to use NumPy. So matplotlib for some visualizations. Seaborn for some visualizations. So now I'm going to load the dataset. So in datasets module, you can download many datasets. So ours is MNIST. So it should be MNIST. Then you have to pass where to download. So I'm going to download in the current location. So I have to use dot download equal to true. So I'm going to download the training data. So train equal to true. Then I need to convert those images to numbers. So I'm going to use transform. Transforms dot to tensor. So this to tensor transform is taking some image and then convert to numbers. Train equal to false because this is validation dataset. Transform equal to the same transforms. So it's downloaded. So this MNIST, I'm going to see first data. So MNIST train of maybe 2000. So it returns two tensor. So first one is image in numerical form, and then second item is which is the label. So this image belongs to the label 5. Maybe we can quickly visualize. MNIST 2000. IF show. So this number image is 5. So it says 5. So maybe let's check one more item. 1000. So 1000 is 0. So here we have cases from 0 to 9. So so it's like a 10 class classification. Now I am going to convert this to binary classification. I'm going to pick just two numbers and then use it so that we can visualize much better. And also it trains faster for today's class. So I'm going to reduce the table label size, reduced label. So I'm going to pick 3 and 7. So 3, I'm going to call 3 as 0 and 7 as 1. Then iterate the training data and then select only 3 and 7. So image comma reduce label of label for label, sorry, for image comma label in MNIST train if label in 3 comma 7. So what it's doing is it's doing some iteration here for image comma label in training data. So if label is 3 and 7, what it does is select image and also transform the label. So if it's 3, go to this dictionary, and 3 returns 0. So it should be image comma 0. So I'm going to do the same thing for validation dataset. So MNIST valid. I can copy paste. So now we have datasets. We are going to create a model. Before going to create a model, I'm going to use data loader. So what data loader is? 1 second, I'm going to explain this. So in our training datasets, we have 12,396 data points. So each data is a 28 by 28 shape. So this is our model. So we need to pass all these images to the model and get predictions, y predictions, and compare this with y and calculate the loss, and then update the bias and weight here in the model. So that's the goal. So the issue here is we have so many images, but I can't load all those images and then do lots of matrix multiplications because I have a GPU memory limit. So my GPU is just 16 GB RAM. I can't load all those images and train a model. So what I can do is I can take some batch of the image, batch, for example, take 64 image, do this, repeat this again and again. So I'm going to randomly select some data, 64 data, and then do to do one update, and then repeat the same thing all until we go all the data. So that's the goal. So we are going to use data loaders. Train loader. So I have to pass the dataset, which is mnist train, then batch size. So I'm going to use 64, shuffle equal to true. Batch size equal to 64, shuffle equal to false. So why I am shuffling in training and not shuffling validation? So in training, uh, our model may memorize if the data set we pass in the same order again and again. So what we are going to do is randomly select some image and put those images to the model and get predictions, then correct the weights and biases. So we'll get some lots of variations here. So that's why we're using shuffling here. Otherwise, our model may just memorize the dataset. So, okay. So we have prepared the datasets. Let's visualize the dataset pl.im show mnist train. So this is 3. I'm going to visualize one more image. Maybe 2000. Okay, this is 7. Okay, this is 7. So our dataset is in good condition. So now we are going to create a training loop. Sorry, before that we are going to create a model. So I'm going to quickly create a model. So let's say this is image 7. Now our goal is to extract many information from this image, which is the input. Extract information. In machine learning, we call this is feature engineering. Extract features. So what is extracting features? Maybe instead of using a neural network, what I can do is I can create some kernels to detect whether this image has any horizontal line or not. I can also create another kernel to find whether this has any diagonal lines, then maybe vertical lines, other edges. So which is very time consuming, which means I need a domain knowledge to create these handcrafted filters. We call kernels as filters, both the same. So these filters extract some information from this image, like pattern. And then we can create like many patterns. For example, for this image, we can create 10 different filters. That's one layer. And then we can create another 5 filters. Then we can reshape everything, which means flattening. Then get predictions. So this is our input. From input, I create 10 filters and then again create 5 filters and then flatten my activations and then make some predictions. So what is the problem here? So let's say this is input image 28 by 28 and we have a huge truck here. Let's assume this is a truck, and the problem here is our kernel size is very small, 3 by 3. So what I do is I take this 3 by 3 and then traverse from here and then again here, 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 and find if there is any pattern here. For example, let's say this is a horizontal edge detector. In this case, I traverse all the images, all over the images and find if there is any pattern. For example, in truck, we may notice a odd pattern here, here. So this kernel 3 by 3 will activate those things. So this is one information. We call this as activation maps. So let's say this is image 28 by 28. After applying 28 by 28 to 3 cross 3, we may get 26 by 26 image. So I'll explain why it's happening here. Before that, I'm going to explain the big issue here. The issue here is these kernels are good at picking small patterns in the image because it's very 3 by 3 image. So what we are going to do is after creating this activation maps, we will reduce this activation maps size to by half, maybe 13 by 13, so that we can get some big picture. So kernel picks small patterns and for big picture we use match pooling. So match pooling is just reducing the reducing the activation maps into smaller size. For example, if it's 26 by 26, if we apply some match pooling, we will get 13 by 13. So we are going to apply some match pooling. So now let's say what is match pooling. Actually, it's pooling. People normally do match pooling. We can also do average pooling. Before that, let's see what is match pooling. Let's say this is our activation map, which has 2, 20, -2, and 11. If I apply match pooling to this list, I may get just 20. So which is maximum of these four numbers, which is 20. So this is match pooling. I can also take average. That's average pooling. So this pooling is helpful to get big picture view, and these kernels are good at getting some minute patterns in the data. For example, whether this image has any diagonal edges or vertical edges, those kind of things. So now I'm going to talk about why this 28 by 28 reduces to 26 by 26. Before that, let's do some visualizations. So if you see this is 4 by 4 image. This 4 by 4 image is going to be 2 by 2 output, and this, if you see the dark one that's moving, that's our kernel. So here the kernel size is 3 by 3. So if it's 3 by 3, 1 second. So if you see the left image, that's image size is 4 by 4. And kernel, which is 3 by 3. You can see it here. This is 3 by 3. The one is moving, that's 3 by 3. So if I apply 3 by 3 kernel to 4 by 4 image, you can see two direction here and two direction here. That's it. So the output should be 2 by 2. So this 4 by 4 reduced to 2 by 2 by applying 3 by 3 kernel. So if you don't want to reduce this loss, for example 4 by 4 changes to 2 by 2, but now let's say I want 4 by 4 and I'm going to apply 3 by 3, but still I want 4 by 4 output. So how to do that? What I can do is I can add some empty layers around this image. So I can increase this size a little bit, one in each side. So I increase the size by 1 in both dimension, height and width increased by 1 plus 1. So what it means is this size should be 6 by 6 because I added one in left and one in right. The same with top and bottom, so it should be 6 by 6. Then if I apply 3 by 3 kernel, I'll be getting 4 by 4. So this concept of adding some empty stuff around this original image, this is called padding. So you can see it here. Here they added padding 2. So this convolution is just a dot product. For example, if I'm calculating this one, what it does is, let's wait for this. Okay, it's here. So here I'm looking just this area, and by looking this area, I multiply my input with this kernel, which is just a dot product. So this is how CNN learns some local patterns in the data. So now we understand what is kernel and what is padding. The next one is stride. So if you notice this, it's moving 1 pixel at a time. It's moved from here, it's going here, and then next. So it's 1 pixel. If I do 2 pixel, which means I'm using stride equal to 2. That's it. So here I am using stride equal to 2. See, I'm jumping after 1 pixel. It's here, then here, here, then here. That's it. I think now we know about kernels, pooling, stride, kernel size, max pooling, and activations. So I'm going to talk a little bit about activations now. So neural network, if you see a neural network input, let's say input is x. So I'm going to compute a function, linear function, which is f of x. So this is layer 1. I'm going to create another one, another layer. In another layer, I pass this output. So this is layer 2, maybe I'm going to f1. Then I pass this same to another function, f2. So this is a linear multiplications, again and again doing lots of linear multiplications. So if we do this, you won't learn any complex patterns, we will learn only linear patterns. To learn some complex patterns, what we can do is we can add some activation functions, which is a non-linear function. For example, y equal to wx. So this is linear. I can make this to non-linear if I apply some activation functions like sigmoid. So sigmoid changes all this output value to 0 to 1 range. So that's what sigmoid function does. In the same way, there is another function called relu, so which is just max of 0 comma x. This is another non-linear functions. So by combining lots of linear and non-linear functions, we can learn any functions. Let's say your data is like this. By combining lots of linear and non-linear layers, we can learn to map this pattern. But if you're using only linear pattern, you will never learn patterns like this. You will just learn patterns like this, only linear. So non-linear activation functions are very helpful in learning some complex patterns in the data. I think now we have all the building blocks to create a convolutional neural network. We'll quickly create a neural network and do some visualizations. I'm checking YouTube. Okay, all good. So I'm going to create a neural network, convolutional neural network. So I'm going to use nn.module as a superclass. So before creating a neural network, I'm going to quickly draw what kind of neural network we are going to create. So this is our input, and we can create a first layer with con1. This con1, maybe we can create some 9 filters, then add relu, and then match pooling, then again create some 18 filters. I'm going to call this as count2, then again relu, which is non-activation functions, non-linear functions, and then max pool, and then we reshape this data. After reshape, you will get some dimensions, then create a fully connected neural network, maybe some shape with 32, then relu, then 32 comma 2. Why it's 2? Because our neural network has to predict two outputs, one for probability of 3 and one for probability of 7. So we haven't talked about fully connected layer at the end. So what's the use of this fully connected neural network? So if you see our architectures, there's a fully connected neural network. So this fully connected layer, what it means, I'm going to give you a quick condition. Let's say this is image 7. Maybe your kernels are good at predicting some patterns. Maybe one kernel is predicts horizontal edge and another predicts diagonal edges, and another predicts whether this image has any circles, those kind of things. So you will get high activations for this layer and this kernel, and high activations for this kernel, but you won't get any activations for this kernel. So our fully connected neural network has some layers. It tries to find some patterns in these kernels and then assigns to some output, like whether this is 3 or 7. I hope this is clear. So we are going to create. So this is 9 filters and then 18 filters, then 32 and 2. Let's create that. Self dot count1. So it takes one channel because our image is black and white, grayscale, and we are going to create 9 filters with shape 3, 3, and then stride equal to 1, padding equal to 1. Why I'm not getting autocomplete? Okay, I didn't import nn. Import torch.nn as nn. Okay, all good. Then maths pool layer self dot maths pool layer nn dot maths pool 2D with kernel size 2, so it reduces our input image into divided by 2. So if it's 28 by 28, we will get 14 by 14 after applying maths pool layer. Then again another maths pool for convolutional 2. So here our input image is 1 comma 28 by 28. So I'm going to explain how to fill these numbers. So our input is 28 by 28, and then what we did is we created 9 kernels with 3 by 3. So 3 by 3 kernel, 9 kernels. So if I apply this 3 by 3 kernel to 28 by 28 image with stride 1 and padding 1, we will get 28 by 28 output. After applying maths pooling, we will get 14 by 14. So after con 1 and maths pool 1, our input image should be 14 by 14. Then after applying con 2 and another maths pooling, we will get 7 by 7. So our input image should be 7 by 7 at the end, and it has 18 filters, so it should be 18 multiplied by 7 into 7. Then we are going to create 32 neurons, and self dot fc2 equal to nn dot linear of 32 comma 2. So here I am going to pass our input image to con1, so self dot con1 of x, and then do nonlinear layer torch.relu, then pass it to maths pool layer self dot mp1, now pass it to self dot conv2 of x, then do another nonlinear activations torch.relu, then put it to self dot maths pool layer. Then fully connected network is x. So we need to pass this input image. So initially it should be any batch size. So I'm going to use -1. We don't know the batch size, so ours is 64. I can directly enter 64, but if I enter -1, it will automatically find the batch size. Then it should be 18 multiplied by 7 multiplied by 7. Then put it to relu torch dot. Then self dot fc2 of x. then return x. I think our model is ready. So I'm going to create model equal to CNN. So currently this model is in our CPU. We need to put this to our GPU so we can optimize it very fast. So I'm going to call CUDA. Okay, so this is our models. So now we are going to, maybe I will quickly check if my model gets some output. So it should return some logits because we are going to use cross entropy. So our model should return some logits. So logits means some real output, not not a probability. It's a real number. So it should be anything like -22 or -1 or 1. It should be any number. Let's check that. So I'm going to give some data to our model. So I'm going to train 0 of 0. So our model expects everything as a batch. Currently this one image is not a batch. So I'm going to add uh, one more shape to the model. So to the input data. So it should be batch, comma, channel, comma, height and width. So currently our model is in GPU, but our data is in CPU. We need to put this to GPU so that it computes. So we are getting this output. Currently this says this input is 3. It's a random numbers. After training, these numbers should be very meaningful. So our model works. Now let's write a quick training loop. So I'm going to write a training loader for image comma label train loader. Put this image to CUDA and label equal to label.CUDA. Then make predictions. And calculate loss. Before calculating loss, we need to define what is our loss and what is our optimization functions. So let's define our loss. So in PyTorch we call loss as criterion, cross entropy loss, and optimizer. So I'm going to use a small learning rate. Then calculate the gradients. If you use loss.backward, it will calculate the gradient for you, and then we can update the gradient by using optimizer.step. After updating the gradients, we need to zero the gradient, otherwise it will accumulate. So our training is done. So for every 2 epoch, I'm going to calculate the validation datasets results so that you know how well our model is training. So we are going to report a accuracy metric. So accuracy is number of correct divided by total number. So correct initially should be 0 and total initially should be 0. for image comma label in valid loader. So it gives some prediction, which is some probability value. So it should return some numbers like this: 0.2, 1.1, again minus 2.08. So it should be tenses. So we have to calculate for this dimension, which is maximum. So predictions are torch.orgmax of ypred in axis 1. So predictions are ready, and also you know the label. If label and predictions are same, which means that's correct, otherwise it's wrong. So now I'm going to count how many are correct. If predictions and label are equal, then that's correct. I'm going to correct total and then add this to our correct numbers. Total plus equal to maybe length of label, print epoch, correct, divided by total. I think that's it. We can train the model. So this is very simple data set. I think in 8 or 10 epoch, we are getting like 0.99% accuracy, which is almost 99% or 100% accurate, because this is a very simple problem, 3 or 7. Our neural network quickly learns some patterns to find whether some image is 3 or 7. So okay, so far we have loaded some data set and then have written a quick convolutional neural network, and then where I have written some training loop, and our model trains, and it will predict any number with high probability. So now let's say we are going to understand what each layer it's learning something. Before that, I'm going to print our model. So this model has conv1 and conv2. So model dot conv1 dot, this model conv1 should have some weight. So each weight is some kernel. Each kernel is good at predicting some pattern in an image. Let's try to understand what these weights mean. So shape, which is 9 filter. Each filter is 3 by 3 image. So what I can do is I can grab some image, maybe image equal to mnist train 0, 0. Put this to a batch and put this to CUDA. Then I can pass this image to the model. Image, it says this is maybe I need to detach this. So this is 3. We are getting high probability for 3. So first is 3, second is 7. Maybe you can use some other image like 1000. For 1000, we are getting high activations in this side, so it should be 7, which is 7. Okay. So we can directly grab this weight. So model.con1.weight.shape, and also I'm going to quickly check model.con2.weight.shape. So this is just one channel. For one channel, I can directly pass our image and get the activation results. But for here, this is 9 channel. I can't pass some 9 channel image and get some results. We can easily visualize this one. But to visualize these kernels, we need to understand some concept like hooks. We'll quickly go through it. But now I'm going to quickly visualize con1 layer, because con1 layer expects channel as 1, but con2 layer expects channel as 9. So I'm going to visualize first one. So first one has con1 has 9 kernels, so it should be 4i in range of 9. What I'm doing here is I'm passing this image to the model, which is just con1 kernel. So this con1 kernel should return some shape, which is con1 res.shape. So which is 9 kernel with 28 by 28 shape. So what I'm going to do is I'm going to visualize these results. Con1 result of 0 of I. It's 0, comma I. Okay. So each kernel is good at picking some pattern. Since our dataset is very small, I think our model learned to map patterns like 7, which is funny. I think this kernel is good at predicting vertical edges. Maybe this is good at predicting horizontal edges. Maybe I can use one more image. 2000. So this is again 7. Or maybe we can use 3. Okay. So this is 3. I think here it tried to learn some patterns around the corners. You can get high visualizations here. I think here is its vertical edges. Here it's horizontal mostly. Here it's some corners, curve. Here is strongly this pattern. think it should be 7. Okay, so now we have visualized con1 layer. Now let's try to visualize con2 layer. But con2 layer expects 9 channel, but we can't create a 9 channel image and put it to con2. But what we can do is there is a concept in PyTorch that's called hook. We are going to use hook and get the results. So hook is like I can create some hook and put it to the model. For example, if I create some hook around con2, it learns what's input and output around this area, and we can store these results to some list, and then we can use those two visualizations. Do we all have the same 9 kernels, or are they random? So initially that should be random, then after some training it learns some patterns to pick up. So each kernel is good at predicting some patterns. So now I'm going to create a visualization pattern for con2 and then final layers. So we are going to visualize con1 maps. So I'm going to call this as, these are activation maps, con1 maps, empty list, con2 maps, empty list, then final input and final output. So we are going to create some hooks. So hooks is just like a function. So def con1 active maps, self input output. Print. So our input should be always a tuple, so we can use input.0.size, print output.size. Then I'm going to, for con1 maps dot append, I'm going to put this output to the above list. So I'm going to repeat the same thing for con2, which is con2 maps. Then again for maybe fully connected FC results, input shape, output size, final input, of 0, final output dot append output. So we have created some functions. Now we have to register these hooks to a PyTorch. So what we can do here is model dot con1 dot register forward hook. For con1 we can use this function. It's done. Then model dot con2 dot register forward hook con2 active maps. Then fully connected networks, model dot, let's check our model. So con1 con2, that's done. then maybe fully connected to FC2 forward, register forward hook. The function name is FC results. I think hook is ready. Now what we can do is we are going to put some image to the model, and our hooks will try to find these things. We will get some print, and then we'll put these results to these maps, and then we can visualize these maps. Let's see. So initially our input size is 1, 1, 28 by 28 because this is one batch, and grayscale, height and width is 28 by 28, and then in con1, which is we'll be getting 9 filters, and after applying match pool we'll get 9, 14 by 14 because match pool reduces this input shape, and then the con2 we are getting 18 filters with 14 by 14 as input, and then these two things are the last final layers, which is this 1, 32 is input and 1, 2 is output. And this model returns 6 and -5, so this should be 3. Now we have collected all the activation maps. Now we are going to understand these things by some visualization. Let's see what it learns. So I'm going to quickly write a plot function, plot convolutions. It takes some conv list. So this conv list is batch, channel, height and width. So we can extract these things, n, c, h, w equal to con list dot shape. Now we are going to reshape conv list equal to con list dot view of c, h, w. For I in range of C, which is kernel, I'm going to show the image. Con list of I. CMap equal to gray. After showing, I'm going to create another figure. Okay, let's run this. If we get any errors, we will debug and fix it. Okay, let's see. PLT convolutions. I'm going to pass our con1 maps. So which is just a list. Just one item, so it should be con1 maps of 0. Okay, I need to put this image, it's in GPU so that I can detach it and put it to CPU. Okay, so our input image is this 3. Maybe I can print one more time. Okay, so this is our input image. So Con1 has 9 kernels. Let's see, each kernel is picking up something. Maybe this kernel is good at predicting edges around here. So this looks almost similar, but there is more activations around these corners. Now let's see what our Con2 is doing. Con2 maps. So in Con2 maps, we are getting good activations around this area. Maybe this kernel is picking up some patterns like for 3. Maybe this kernel is good at predicting some 7. That's why we are not getting any activations. This belongs to 3. Maybe this belongs to 7. You can see some vertical edges. I think this belongs to 7 too. You can see some horizontal edge here, and in 7 you will get more activations here. And this is belongs to, I think, both 3 and 7. This is clearly 3. I think this belongs to 7. Okay, so now try to visualize what our activations are doing. So I think the list name is final output. So now let's check what is final output. So final output is just 2 activations. One is for 3 and another is for 7. There is no use of visualizing this one. Let's visualize the what is input, final input. Okay. So we are getting more activations in many area in this image. I think these 32 neurons are good at predicting. In 32 neurons, some of the neurons are good at predicting 3. So that's why we are seeing some activations, some high activations here, and there is no activations around these areas. Now let's try to pass one more image, that's 7, and see how this changes. Maybe I can directly change here 2000. This is 7. Let's try to pass this. So if I run this code, our list should be updated. So we are going to see activations for this 7. So this is convolutional 1 maps. Let's visualize count 2 maps. I think this kernel mostly belongs to 7. This is 3, 7. Maybe this is 3. So this belongs to 3. I'm going to do the same thing for 7. See, it's almost the opposite. I think these neurons 16, 18, 16 to 20, they are good at picking up some patterns that belongs to 7. You will see more activations here. I think I'm going to share this code on Slack. In this class, we have created some models, and also we have did some visualization, try to understand more about the data. Maybe you can, I have used a simple data set called MNIST. There are so many data sets available on datasets module. You can, instead of MNIST, you can use CIFAR 10 and train a model and try to visualize and understand more about your datasets. Maybe you can do this an exercise, and if you have any issues, you can post it on Slack and also on YouTube. In the next session, I think in the last few sessions we have covered mostly about convolutional neural network. In the next session, we will see some applications of convolutional neural network. We will download some real data sets and then try to run some state-of-the-art models, and then we will dive into recurrent neural network that's mainly used for text classifications and text generations or time series datasets. I think I'll see you in the next class. Before that, I'll share this notebook with you all. I think I'll share this in a few minutes. If you have any questions, please ask on Slack. I'll wait for 2 to 3 minutes and then end this uh, live stream. Thank you, everyone. Thanks, everyone. See you next week.